In this problem, we have to determine what type of filter the network shown below represents by determining the voltage transfer function. And that transfer function will be V0 of S over Vi of S. Now to start, can do is let's simplify this circuit some, and then we can use voltage division and start from there. So if we look, we have two elements in parallel. We can combine those as admittances by adding admittances. So we have 1 over R2 plus 1 over SL, and that can be rewritten as SL plus R2 over SL R2. And we really need to convert that to Z because we're going to be using voltage division. So we have SL R2 over SL plus R. And if we divide out, if we factor out an L, this becomes SR2 over S plus R2 over L. Now let's redraw our circuit showing that. Okay. So here's our circuit showing our combination. So now, using voltage division, V0 can be written in terms of Vi, so we have SR2 over S plus R2 over L divided by R1 plus S R2 over S plus R2 over L times Vi. So now we can get that from voltage division, and we can get it into the transfer function form simply by dividing 3 by Vi. And so we have SR2 over S plus R2 over L. Then we have R1 plus SR2 over S plus R2 over L. Now it's just going to be a matter of some algebra at this point in time. We need to get this into a form that we can begin to decide what type of filter it is. So for instance, let's take now, multiply the top and the bottom by S plus R over L, S plus R2 over L, and multiply this by S plus R2 over L. So we're going to now multiply it by 1. And if we do that, we'll have S plus R2. We'll have R1 times S plus R2 over L plus S times R2. And rearranging, we'll have SR2 over S times R1 plus R2 plus R1 R2 over L. So again, now we're just working through the algebra, and we can factor out an R1 plus R2 out of the denominator term, so we can write this as R2 over R1 plus R2, and then we have S over S plus R1 R2 over R1 plus R2 L. And if we continued on, for instance, we could get this into our standard form. As well, if we really look at it here, we really notice we've got a 0 at the origin, and we've really got a simple pole at some frequency. And if we took that, for instance, and said, well, what about the characteristic of those two terms? So we know we've got a 0 at the origin and a simple pole. So we know for a 0 at the origin, for instance, we know the magnitude characteristic is something like this. It has a gain of 0 at omega equal 1. So we have omega in radians per second. We're sketching with a log scale. We know it has a slope of plus 20 dB per decade. So it has 0. We also have a gain expression out here. I'm not going to worry about that too much, but we have a simple pole, and we know for a simple pole that we know it starts off at 0 dB, comes out, and at some point it breaks down at minus 20 dB per decade. And we also have, like I said, we have a gain term, but we're not too worried about that. If I look and plot kind of a rough sketch of for this filter, you know what's going to happen is the 0 at the origin, we're going to be coming up at plus 20 dB per decade. And when we reach the frequency of that pole, that's going to go down at minus 20, so it's going to flatten out to be a characteristic like that. And if we look at our filter characteristics, that's a high-pass filter.